Before hydraulics changed construction forever, there was a machine so important, so brutally effective, that one of the largest equipment manufacturers in the world could not work without it. In the 1930s and 1940s, Caterpillar crawler tractors rolled off the assembly line looking complete. Massive steel tracks, roaring diesel power, raw industrial muscle. To anyone watching, they looked ready to conquer mountains, but they were not. Without one specific attachment bolted to the rear, those machines could not truly cut dirt. They could not properly raise a blade. They could not lift a scraper bowl. They could not do the work history remembers them for. They were, in the harshest possible terms, just engines on tracks. That is the first shock in this story. Because for nearly an entire generation of heavy construction, some of the most powerful machines on Earth depended on a hidden mechanical system most people have never heard of. A cast-iron cable control unit designed by LeTourneau. And that raises a question almost nobody asks. How does one machine become so essential that even Caterpillar could not easily replace it? The answer is stranger than it sounds. At the height of its power, LeTourneau's cable control system did more than move dirt. It quietly controlled the working life of bulldozers, scrapers, blades, and earth-moving attachments across dams, highways, military bases, and wartime airfields. It helped transform tractors into real earth movers. It made giant machines obey. And yet, the very thing that made it powerful also made it terrifying, because this system relied on steel cable under extreme tension, not hydraulic pressure, not sealed cylinders, not smooth controlled force, just gears, drums, levers, and a living line of wire rope stretched tight enough to lift steel, drag earth, and, if something went wrong, snap back with enough violence to kill in an instant. Imagine sitting on an open crawler tractor in rough ground, no cab around you, no safety cage above you, no protection at all, while a half-inch steel cable behind your seat screams under load. Every time you pull a lever, you are not just controlling a machine, you are negotiating with force. And that force built more of the modern world than most people realize. It shaped roads before highways. It carved dams before hydraulic blades took over. It helped military engineers build airstrips where jungle stood days before. It gave crawler tractors their real purpose in an age before fluid power could be trusted. But here is the darkest part. The men who mastered these systems often describe them with the kind of respect normally reserved for dangerous animals. Because if you understood the cable, the machine worked with you. If you misread it, it punished you immediately. So what exactly was this machine? How did it work? Why did it dominate heavy construction before hydraulics? And why did an invention this powerful vanish almost completely from the modern world? To answer that, we have to go where few people ever do. Not to the job site, not to the boardroom, not yet. First, we have to open the iron box behind the operator's seat. What made LeTourneau's cable control unit so extraordinary was not how dramatic it looked, but how much hidden power it concentrated into one brutally simple machine. To the untrained eye, it was just a heavy cast-iron box bolted behind the operator's seat on a Caterpillar crawler tractor, usually coated in oil, dust, and the kind of hard-packed grime that only comes from real earth moving. It did not have the polished look of modern hydraulics. No chrome cylinders, no gleaming hoses, no sleek engineering theater. It looked crude, overbuilt, almost primitive. But that appearance was deceptive. Inside that iron housing was the mechanical heart that transformed an ordinary crawler into a true working earth mover. Without it, a tractor could move itself. With it, it could move the world. That is the second shock in this story. The machine that made bulldozers, scrapers, and blades truly useful was not the tractor itself. It was the control system hidden behind the driver, pulling power directly from the machine's transmission like a parasite feeding from the strongest artery in the body. LeTourneau did not design this unit to borrow spare power. He designed it to take force straight from the tractor's core. Once engaged, gears inside the housing transferred that power into rotating drums, and those drums wound or released steel cable connected to blades, scrapers, and towed equipment. In modern terms, this was the nervous system of the machine. Every lift, every drop, every pull, every hold depended on what happened inside that box. And yet, the way it worked was brutally mechanical. There was no soft actuation, no forgiving delay, no smooth hydraulic cushion, just geared teeth meshing in oil, steel cones biting into each other under clutch pressure, and spring-loaded brakes ready to clamp the moment a lever returned to neutral. Push the lever one way, and the drum hauled cable in tight, raising a blade or lifting a scraper bowl. Let go, and the system snapped back to center. Pull the lever the opposite way, and the brake released, allowing the cable to spool out under gravity. That simplicity is what made the system brilliant and dangerous, because every movement depended on force, friction, and timing. There was no electronic protection, no sensor to stop an overrun, no backup logic. The operator's hand was the computer. His instincts were the safety system. And that is why the power control unit mattered so much. It did not just add an attachment to a tractor, it changed what a tractor was. It turned tracked horsepower into controlled earth-moving force. It gave contractors a way to raise blades, pull scrapers, and control heavy implements years before reliable hydraulics could survive dust, grit, shock loads, and constant abuse. In a world before fluid power could be trusted, this machine became the bridge between raw engine power and useful work. But buried inside that brilliance was a fatal limitation, because no matter how perfect the gears were, no matter how clever the clutch design, the entire system still depended on one unforgiving truth. Steel cable can pull with terrifying strength, but it cannot push back, and that weakness would eventually change everything. The real genius of LeTourneau's cable control system was not just that it worked, it was that it solved a problem nobody else had solved at scale in the brutal conditions of early earth moving. Before hydraulics became reliable, heavy equipment needed a way to control blades, scraper bowls, and attachments under shock, dirt, heat, vibration, and constant abuse. Most systems of the era simply could not survive that punishment. Hydraulic technology existed in limited forms, but seals leaked, fluid systems failed, and contamination could cripple performance in exactly the kind of hostile environments where crawler tractors were expected to work. What contractors needed was not elegance. They needed something that could be dropped into mud, rattled across rock, run all day under load, and still keep functioning with the kind of stubborn reliability that built roads, dams, and military infrastructure. That is where LeTourneau's design became almost unstoppable, because unlike early hydraulic systems, the cable control unit was built for the world as it actually was, dirty, violent, unpredictable, and unforgiving. Its strength came from mechanical directness. Power flowed from the tractor's transmission into gears, into drums, into wire rope, and then straight into the working tool. There was almost no mystery in it. Operators could hear it, feel it, and understand it. If the cable tightened, the blade rose. If the brake released, the blade dropped. If something began to bind, the machine told you in noise, vibration, resistance, or heat. It was not hidden behind fluid pressure or sealed circuits. It was visible force, translated through steel. And in the construction world of the 1930s and 1940s, that mattered more than modern engineers might realize. On remote job sites, the ability to diagnose a machine by sound and touch was not a convenience, it was survival. A broken hose in a modern hydraulic system might mean waiting for parts. A worn cable, a slipping clutch, or a dragging brake in a LeTourneau unit could often be understood and repaired by men who lived with the machine every day. That made the system not only powerful, but field practical.
And that practicality is why it spread so aggressively. Contractors could mount these units on crawler tractors and suddenly perform tasks that would have been painfully slow, expensive, or impossible by hand. Scraper bowls could be lifted, dozer blades could be controlled, towed implements could be manipulated with surprising precision. Entire categories of earth moving became faster, more repeatable, and more profitable. That is why the system did not merely survive, it dominated. It became the hidden standard of an era when the world was being physically reshaped at industrial speed. Roads expanded, airfields appeared, military engineers pushed into impossible terrain. Massive civil projects demanded equipment that could take punishment and keep moving. And again, the answer was not a futuristic fluid-powered breakthrough. It was an iron box, a drum, and a line of cable under tension. But even as this system conquered the job site, its greatest advantage was quietly becoming its greatest weakness. Because the more construction demanded precision, speed, and safety, the more obvious one brutal fact became. A cable system could pull with immense strength, but it still forced men to work around the violent limits of gravity, tension, and exposed steel. And the closer the industry pushed toward bigger machines and tighter control, the closer LeTourneau's masterpiece moved toward the edge of its own extinction.
For all its brilliance, LeTourneau's cable control system carried a weakness so fundamental that no amount of clever engineering could ever fully eliminate it. A steel cable can pull with tremendous force, but it cannot push. That single limitation shaped everything about how these machines worked, and it is the reason this once dominant system was always living on borrowed time. When the operator pulled the control lever, the rotating drum could wind cable in and lift a blade, raise a scraper bowl, or haul an attachment upward against gravity with shocking efficiency. But when it came time to lower that equipment, the machine could not actively force it down. It could only release tension and let gravity do the rest. That meant every downward movement depended not on precise mechanical control, but on the weight of the implement itself, the slope of the terrain, the amount of packed soil clinging to the blade, and the operator's timing. On flat ground, that might be manageable. On rough ground, sticky clay, uneven cuts, or steep grades, it could become unpredictable fast. A hydraulic cylinder can both lift and push downward with controlled pressure. A cable system could only lift and then hope gravity behaved. And on a job site, hope is a dangerous design principle. This is where the hidden instability of the system started to reveal itself. If a blade was too light, it might not drop quickly enough. If it was packed with mud or dirt in the wrong way, it might hesitate, jerk, or fall unevenly. If the machine hit changing terrain at the wrong moment, the operator had to react instantly with nothing but lever feel and instinct. There was no smooth, balanced, bidirectional force, just lift under power and drop under release. That sounds minor until you imagine what that meant in real work. Earth moving is not just about strength, it is about precision. The operator is constantly adjusting cutting depth, angle, resistance, and tool position. A system that can only power one half of that movement forces the man in the seat to fight the machine as much as control it. And the larger the projects became, the more punishing that compromise looked. Contractors wanted cleaner grades, faster cycles, tighter control, and safer operation. They wanted machines that could press a blade into hard ground, not just let it fall there. They wanted scraper bowls that could be forced into position, not simply lowered and managed. They wanted predictable motion, not motion partially surrendered to gravity, terrain, and timing. And then there was the danger no one on those job sites could ignore, the cable itself. Every function depended on steel wire rope under brutal tension, constantly winding, unwinding, flexing, rubbing, and carrying shock loads through pulleys and drums. That meant wear was not theoretical, it was inevitable. Cables frayed, strands broke, tension changed. A line under load could snap with explosive violence, and when it did, it could whip through open air like a steel lash. In an era of exposed operator stations, minimal shielding, and almost no modern safety standards, that risk was never far away. Men who worked these systems respected them the way soldiers respect live artillery, because they understood that a machine this useful could become lethal in a fraction of a second.
And once the industry saw a better alternative coming, one that could lift and push downward, hold and lower, seal power inside protected cylinders, and remove the chaos of exposed cable, the countdown had already begun. LeTourneau's masterpiece was still strong, it was still working, but for the first time, it was no longer the future.
By the late 1940s and into the 1950s, the construction industry began to witness something that had seemed almost impossible just a decade earlier. Hydraulics were no longer fragile experiments. They were becoming a real threat. For years, LeTourneau's cable control system had dominated because it matched the brutal reality of early earthmoving better than anything else. It was strong, repairable, familiar, and brutally effective in the dust, shock, and punishment of the job site. But now, a new kind of power was arriving, one that did not rely on exposed drums, steel wire rope, gravity-assisted lowering, or an operator's constant battle with tension and timing. Hydraulics offered something the old cable systems could never truly deliver: full two-way control. For the first time, a machine could not only raise a blade or scraper bowl, but force it downward with equal authority. It could hold a position under pressure. It could make smaller, smoother, more precise adjustments. And perhaps most importantly, it could do all of that without exposing the operator to a live steel cable stretched under dangerous tension just inches away. That shift was not just technical, it was psychological. Once contractors and operators experienced what it felt like to command an attachment that moved in both directions with fluid pressure rather than lifting under power and dropping under gravity, the old system immediately began to feel like a relic from a harsher age. What had once seemed ingenious now started to feel exhausting. What had once seemed powerful now looked crude. And that is how great technologies die. Not because they suddenly stop working, but because something better changes the standard of what good feels like. Hydraulics changed that standard overnight. Blades could now be pressed into the ground instead of merely lowered toward it. Scraper bowls could be positioned with greater confidence. Fine grading became easier. Cycle times improved. Operator fatigue dropped. Safety improved. Maintenance, while different and still demanding, increasingly looked worth the trade-off because the performance gains were impossible to ignore. Manufacturers saw it too. The industry was growing fast. Projects were becoming larger and more complex, and contractors wanted machines that required less guesswork and delivered more precision. The very conditions that had once made cable systems unbeatable, rough terrain, heavy loads, constant abuse, were now being met by hydraulic designs that had matured enough to survive them. Better seals, stronger components, improved fluid systems, and more refined engineering began closing the reliability gap that had protected cable controls for so long. And once that happened, LeTourneau's old advantage started collapsing from every direction at once. The cable control unit still had strengths. It was still rugged. It was still field-proven. It still had operators who trusted it. But now it carried visible compromises that hydraulics exposed mercilessly: one-way force, cable wear, jerky response, dangerous snapback risk, and a growing sense that the operator was managing the machine's limitations rather than benefiting from its design. In the space of a few years, a system that had helped build roads, dams, wartime infrastructure, and the physical backbone of modern America began slipping toward obsolescence, not because it failed history, but because history moved on. And that is the cruelest truth in industrial progress. The machine that once defined an era can become outdated while it is still doing the job. LeTourneau's cable system had not become weak, it had become old in a world that suddenly demanded more.
By the mid-1940s, the industrial landscape that LeTourneau had mastered for decades was about to face its most brutal test yet. The power control unit, his 600-pound marvel of gears, cables, and brute engineering, had built highways, dams, and military airfields across continents. Yet the very technology that had guaranteed his dominance was now being challenged in ways few could have foreseen. Operators, those fearless men who danced daily with tension steel, understood the dangers intimately. One misjudged lever, one worn cable, and the machine could snap back with deadly force. The statistics were grim. Between 1940 and 1955, nearly 1,800 cable operators perished across American construction sites, victims of fatigue, neglected maintenance, or a simple miscalculation. Each death was a haunting reminder of the invisible balance of power between man and machine, and it underscored a central paradox. The system that allowed them to move mountains was also a machine capable of crushing them. The disaster potential was everywhere. At Hoover Dam, cables snapped under unimaginable tension, sending steel cords like whips into the air. At early motor scraper sites, misaligned sheaves and poorly shimmed drums caused violent jams. Operators nicknamed these machines widowmakers for a reason. These were not merely tools. They were living entities with moods, behaviors, and deadly quirks that had to be respected. Yet it was not just human error. The very design imposed risks. Cable could only pull, never push. A hard surface or uneven cut could send blades skipping, creating sudden, unpredictable forces. The bull-push beams of early scrapers loomed above the operator's head like loaded traps, and when hitches failed, the consequences were immediate and lethal. Every deployment was a high-stakes gamble, a calculated dance with physics. Yet amidst the danger, operators developed a near-supernatural connection to their machines. They could feel a cable about to overwind, anticipate tension changes, and adjust in ways no hydraulic system could teach. But even mastery had limits. Nature, gravity, and sheer mechanical power were indiscriminate. One wrong move, one fatigued hand, and the disaster unfolded in a heartbeat. These moments of peril were the crucible in which the cable men were forged, a mix of skill, instinct, and nerve. The disasters were not isolated events. They were warnings, signals that the next wave of technology, hydraulics, would eventually address the lethal vulnerabilities inherent in cable systems. Yet every snapped cable, crushed hand, or fatal misstep left an indelible mark on industrial history. These were not mere accidents. They were lessons etched in steel, force, and human sacrifice. The machines that had constructed the modern world carried the weight of human lives in their operation, and understanding these disasters is essential to grasping the full scale of the power, danger, and genius behind LeTourneau's invention. In the end, the disasters of cable control were both a testament to the machine's might and a foreshadowing of its inevitable decline in the face of safer, more precise hydraulic technology.
By the late 1930s and into the 1940s, LeTourneau's cable-controlled machines were no longer just engineering marvels. They had become titans that reshaped landscapes and changed the course of construction history. The impact of his inventions stretched far beyond the factory floors of East Peoria and Stockton. They were rewriting the rules of what humans could achieve with earth-moving technology. The Model A Tornapole, his self-propelled motor scraper, proved that entire projects could be completed faster, with fewer machines, and with unprecedented precision. At massive projects like the Hansen Dam in Los Angeles, over 13 million cubic yards of earth were moved with machines operated through nothing more than cables, levers, and the intuition of the operator. These were not just machines, they were extensions of human skill, pushing the boundaries of speed and efficiency. The average crawler tractor pulling scrapers could not compete. LeTourneau's innovations were literally doubling the pace of construction. The war amplified this impact to a global scale. During World War II, his factories produced roughly 70% of all Allied earth-moving equipment, supplying tens of thousands of bulldozers, scrapers, and rollers that built the infrastructure of victory. Airfields, naval bases, and emergency flood control projects all relied on his cable-controlled machines. At Espiritu Santo in the Pacific, a 6,000-foot airstrip was carved out of untouched jungle in just 20 days, an unimaginable feat that would have been impossible with conventional tractors. Each machine carried immense power in its steel cables, yet required an operator's skill and respect. Every lever pulled, every cable tensioned correctly, directly translated to the success of massive construction projects that supported military operations and civilian recovery alike. But the impact wasn't only operational, it was economic and strategic. LeTourneau's technology created a dependency that even the largest manufacturers couldn't ignore. Caterpillar, for all its dominance, relied on his attachments and power control units to maintain production. Governments stepped in to protect the supply chain during wartime, recognizing that a single innovation, the power control unit, was critical to the Allied war effort. The scale of his machine's influence meant that one man's invention dictated the speed of construction across continents, the efficiency of war logistics, and the very shape of modern infrastructure. But this dominance carried a shadow. The same machines that could build entire dams or airfields in weeks were capable of taking lives in a heartbeat. Deadly cable snaps, misaligned sheaves, and fatigued operators turned efficiency into danger. The legacy of these machines was one of paradox, immense human progress built on the knife edge of risk. Every successful project was a testament to ingenuity, while every disaster underscored the fragile balance between man and machine. In the annals of industrial history, few inventions wielded influence on this scale, leaving a mark that would echo long after hydraulics replaced cables, yet whose principles still underpin the largest machines ever built today.
The final chapter of this story isn't just about machines. It's about legacy, human ingenuity, and the paradox of progress. By the 1960s, hydraulics had finally matured, rendering cable control obsolete, and the great power control units that once ruled construction sites disappeared almost entirely. Yet the true legacy of LeTourneau's inventions was never just about the machines themselves. It was about the way they reshaped the mindset of an entire industry. The lessons embedded in every lever, every steel cable, and every operator's hand still resonate. Precision, respect for mechanical limits, and the intimate connection between human skill and industrial power. For decades, operators known as cable men were the invisible heroes of construction, reading tension in a cable as if it were a heartbeat, adjusting sheaves with the meticulous care of a surgeon, and risking their lives daily to push the boundaries of what earth-moving machines could achieve. Their work embodied the ultimate fusion of human intuition and mechanical force. Yet with the disappearance of cable-controlled machines, an entire culture vanished. The skills of the cable men, the ability to feel the pull of a drum, to sense the tension and anticipate a snap, to manage machinery whose failure meant instant disaster, were lost in a single generation. Even the most advanced hydraulics could replicate efficiency, but they could never replicate the artistry of a cable man, the silent dialogue between human and machine that defined an era. The story of cable control serves as a haunting reminder that innovation is never just technological. It carries the weight of those who operate it, the risks they endure, and the fleeting nature of mastery. LeTourneau's vision, however, did not die. He had already transitioned to electric drive technology, skipping hydraulics entirely, and creating machines that presaged the largest diesel-electric mining trucks operating today. His career formed a full circle, from electric to cable to electric again, demonstrating a foresight that only hindsight can fully appreciate. Modern machinery owes a debt to the principles he pioneered: simplicity, efficiency, and an understanding of how to harness mechanical power safely and effectively. In this chapter, we also confront the psychological and moral dimensions of progress. The machines that moved the world came at human cost, from the thousands of deaths on construction sites to the relentless demands placed on operators.
The story of cable control is inseparable from the story of sacrifice. Yet it is precisely these stakes that made the achievements remarkable. Every completed dam, airfield, and highway carried the imprint of human bravery and mechanical genius intertwined. As the curtain falls, the haunting question remains: what has been lost in the relentless pursuit of faster, more automated technology? The cablemen are gone, the machines are gone, but the lessons endure. The legacy of the power control unit is a meditation on mastery, respect, and foresight. It reminds us that progress is not merely about replacing one technology with another. It is about understanding the human stories and risks that lie behind every innovation. And while hydraulics may have replaced cables, the principles LeTourneau championed, precision, resilience, and visionary engineering, still shape the machines that move our world today. This is not just a story of steel and cables. It is a story of courage, foresight, and the enduring human spirit behind every lever pulled.